All right, we're going to begin to go over the open book test on Unit 3.5 and 3.6. And the first part says find each limit if possible. We're trying to find the limits at infinity. So the question is, after spring break and getting back, how do we do that? So what do we do? Well, what we did is we remember this little rule that the limit as x approaches infinity of 1 over x is equal to 0. Now that's kind of where we need to start remembering. And the reason that is because as x gets infinitely large, if you take, like, let's just say we had 8 divided by 1 is 8, 8 divided by 2 is 4, 8 divided by 8 is 1, 8 divided by 16 is a half. You can see as what you're dividing by gets bigger and bigger, the answer gets smaller and smaller and smaller. So as what we're dividing by here approaches infinity, then the result is approaching something infinitely small, smaller, 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 smaller. We're approaching 0. So the limit as x approaches infinity of 1 over x is equal to 0. So we're going to try to turn as much stuff as possible into the form 1 over x. And that will create a bunch of zeros in our problem. Now, we learned some things about asymptotes. So what I'm going to do first is I'm going to show you how to do it algebraically, and then we're going to talk about asymptotes and basically save some time. But we do want to see the proper form. So what we're going to try to do is tweak those into being in that form. Well, to do that in this problem, then we would take the x squared idea. We'd say, well, if we want to turn some things into numbers or in that form, then what we would do is we would divide the numerator and the denominator by x squared. And this is what we would have if we go ahead and show all of our work. We would have the limit as x approaches infinity of x squared over x squared plus 2 over x squared over x squared over x squared minus 1 over x squared. You see we've divided the numerator and denominator by x squared. Sorry about that automatic update there. Okay, so what's going to happen here then is we will have the limit as x approaches infinity of 1 plus 2 over x squared over 1 minus 1 over x squared. So, as x approaches infinity, this is going to be a 1. The second term, as x squared approaches infinity, we're taking some number like 2 and dividing it by x squared. So that's going to approach 0. And then over here we're going to have 1 minus 1 divided by, as x approaches infinity, x squared approaches infinity, and 1 divided by infinity is 0, so we have a 1 over 0. So we end up with a 1 plus 0 over a 1 minus 0. And 1 plus 0 is 0, is 1, excuse me, and 1 minus 0 is 1, 1 minus 1 is 1. So the limit as x approaches infinity of x squared plus 2 over x squared minus 1 is 1. Okay, so there's the algebraic method using the rule that the limit as x approaches infinity of 1 over x is equal to 0. Let's see how we got that. Now let's talk about the asymptote rules. If we think about the asymptote rules, then we would say that the exponent in the numerator and denominator is the same. And when we use the rules of rational functions, then we said that if the degree of the numerator is the same as the degree of the denominator, then what? then there is a horizontal asymptote in a certain place. What will the horizontal asymptote be if the ratio of the leading of the coefficients is the same? It will be the ratio of the leading coefficients. And I said that calculator is 1. So we're going to have a horizontal asymptote at 1. That means if we were to try to graph this thing, there's going to be a horizontal asymptote at 1. And so as x approaches infinity, our graph is going to approach that asymptote. And so the limit, as x approaches infinity, of that function would be 1. That's the idea of the horizontal asymptote. We could graph this on a graphing calculator and verify. And I think we probably should in this discussion, so we have some verification of what all we're doing. So let's put this one in the graphing calculator. We'll try to get that going this morning. So we'll go to our graphing calculator. We'll go to y equal. I'm going to clear that out. And we're going to type this in, open parenthesis, x squared plus 2, close parenthesis, divide, open parenthesis, x squared minus 1, close, and then we'll hit graph and take a look. And you can ignore the dots there, that was from something else. But you can see, as we talked about, that there's a horizontal asymptote at y is equal to 1. And so as x approaches infinity, the function value is approaching that asymptote of 1. I drew it a while ago on the bottom, but the graph actually put it on the top, but the same situation's going on. Any questions on that? So we have graphical verification if we need that graphical verification. Okay? All right. Any questions on the first one? We'll bring all that back. Oops, I wrote on it, so it's not coming back. Okay. Question number 2. How would we approach question number 2 from an algebraic standpoint? Well, we would divide the numerator and the denominator by we can divide by the x. We've got an x. The highest exponent is 3 over 2, but if we want to fix the denominator part, that's the tricky part for us. Then let's just divide by x and see what happens. So we would have the limit as x approaches infinity, of 5 over x minus 2 to the x, and then that 2 to the x is going to divided by x, that's going to be the first, and when you divide with like bases, you subtract, so that would be the 1/2, right? 3/2 minus 2/2 is 1/2 over, and then we've got 3 to the x over x, and then minus 4 over x. Okay, so what's that going to do for us? We're going to have the limit as x approaches infinity. The 5 over x turns into what? 0. The 3x over x turns into 3. The 4 over x turns into 0. And then what does this turn into? Well, as x gets infinitely large, what's going to happen? As x gets infinitely large, my answer is going to get infinitely large. And if you take something infinitely large times 2, you have something infinitely large. But if you multiply it by a negative, you have something that is negatively infinitely large. Does that make sense? And if we take something that is negatively infinitely large divided by 3, we still have something that is negatively infinitely large. So the result is negative infinity, but what are the rules for a limit existing? For a limit to exist, 3 things must be true. Number 1, it must approach the same thing from what's left and from right. And number 2, it cannot approach, well, the oscillating thing, it cannot approach infinity as you approach that point. It cannot approach positive or negative infinity. And number 3, if it oscillates between 2 fixed points as you approach that target point C, then the limit does not exist. So because it's headed into infinity at that target point, we say that the limit does not exist. The limit does not exist. Now, you understand, if we had a situation to where the degree of the numerator was 1 bigger than the degree of the denominator, then we would have a slant asymptote. And if we had a slant asymptote, then as we approached positive infinity, then what would be happening is this would be approaching infinity, so we would say the limit does not exist. Okay? Or if our slant asymptote was like this, then we would say that as this approaches infinity, this is approaching negative infinity, therefore the limit does not exist. Well, the degree of the numerator here is bigger than the degree of the denominator. It's not 1 bigger, so there's not a slant asymptote. But there's also not a horizontal asymptote. And so you think, well, there's not a slant asymptote, and there's not a horizontal asymptote, so what's this thing look like? This must be some weird-looking thing. Well, it's kind of got a square root in it with that divided by 2. So let's just actually graph this and just see what's going on. We've algebraically proved the limit does not exist. There's not a horizontal asymptote, a slant asymptote, everything didn't zero out. So let's take a look at it again, graphically speaking. So we'll pull the calculator back up. We're going to go into y equal and clear that out. Let me go to my stat right quick, and I'll clear my list just to get those dots out of there. Okay, and so we're going to have numerator, which is open 5 minus x,
2x.
oh, 2x, excuse me, 2x raised to the 3 halves, 3 divided 2 close, and then I need to close my numerator, divided by my denominator of 3x minus 4, close the denominator, graph, domain error, second quit, y equal 5 minus 2x to the 3 over 2 divide open 3x minus 4. So we didn't get a graph out of that either, did we? So anyway, having a little trouble even getting a graph from that because of some domain errors. Okay, so, but we've verified there algebraically that we will be reaching the limit is approaching negative infinity. It says to us because of the definition of the limit that the limit does not exist. Any questions on number 2? Okay. Let's look at number 3. Okay, and we're back with the graphing calculator looking at question number 2 there. I knew it should have graphed, so I was thinking, why was there an error? But I needed to turn my stat plots off. I didn't clear my calculator to start with. So you can see that as we approach positive infinity for x, that the y here is approaching, it's going to keep going, so it's going to approach infinity there, but we're on the downside of the graph, so y is getting infinitely negatively large as we go infinitely to the right of the graph. Okay, so we can verify graphically. There is some type of an asymptote that it would be trying to follow there, but it's kind of following in a different weird way there, right? So there's the verification graphically of question number 2. All right. Question number 3. Question number 3, we have the limit as x approaches infinity. Now, how would we approach this situation from an algebraic standpoint? We would divide the numerator and denominator by x cubed. Now, remember when we're doing that, we're distributing, right? In the numerator and denominator. We have the limit as x approaches infinity of 3x cubed over x cubed, if we show all of our work, plus 2 over x cubed over 9x cubed over x cubed minus 2x squared over x cubed plus 7 over x cubed. Let's catch up with the right again. So this is going to simplify into the limit as x approaches infinity of the x cubes cancel there, and we have the 3. And then we're going to have plus 2 over x cubed. And then the x cubes are going to cancel here, and we're going to have a 9. And then we're going to have minus 2 over x plus 7 over x cubed. So we're going to have a 3. As x gets infinitely large, we're dividing by something infinitely large, and so that's going to approach 0. And then we have a 9. As x gets infinitely large, we're getting something that's approaching 0. As x gets infinitely large, we divide, we're getting something again that approaches 0. So we're going to have a 3 over a 9, which is going to reduce to a 1/3. And so the limit as x approaches infinity of that function is 1/3. So that's again the approaching it from an algebraic standpoint. Approaching it from an asymptote standpoint, we would say the degree of the numerator is the same as the degree of the denominator. So there will be a horizontal asymptote at what? 3. Good. There will be a horizontal asymptote at the ratio of the leading coefficients. And that's a 1/3, and that verifies that graphically speaking, we would be hugging up against that asymptote of the 1/3. Therefore, that's what our limit would be. And we could graph that, and you can see that. Any questions on number 3? All right. Well, let's take a look at number 4. Number 4 is a little trig function, and when you look at that, you may say, well, it looks kind of like it's in the form of something over infinity, right? Something over infinity. But if that something on top, what's it doing? Infinity over infinity is an indeterminate form. We can't really deal with that. How could we actually mathematically prove what the sine of 2x over x is? Well, let's think about this. Let's just think about the graph of a sine wave. The graph of a sine wave starts where? And then it's going to go up to, and then it's going to go back to, and then it's going to go down to, and then back up to 0. So that tells me that even if I go into infinity, then this situation, at least in the numerator part, that numerator lies between -1 and +1, right? So we could think of this as a squeeze theorem. If the sine of 2x is between -1 and +1, if the sine of 2x is going to be somewhere between -1 and +1, then the sine of 2x over x is somewhere between -1 over x and +1 over x, right? You understand what we've done? So we're applying the squeeze theorem to this to try to prove what sine 2x over x is. Well, this form gives us a what? A 0, as we talk about x getting infinitely large, -1 divided by something infinitely large is 0. And this form, as x approaches infinity, 1 divided by infinity is 0. So replacing those with 0 gives us that the sine of 2x over x is somewhere between 0 and 0. Well, that forces it to be 0. Any questions on number 4? We use the squeeze theorem to mathematically prove that the sine of 2x over x is 0. Okay? All right. Any questions on number 4? All right. Number 5 says sketch the graph of the function using extrema, intercepts, symmetry, points of inflection, asymptotes. Wow, this one's going to take a good bit of time. I'm not actually going to do it. I'm going to start this on the next video. And we will use, in fact, on this paper, I've got 5, 6, 7, 8. It's probably going to take a whole sheet of paper to do 5 and another whole sheet of paper to do 6. So when I give you the test, I won't have 4 problems per page. I'll have 1 per page. So it's probably going to be wise when we take notes here to maybe get out some notebook paper and do this, because there's a lot of calculation if we show our work here, which we'll do. So anyway, I'm going to stop there, and then in part 2, I'm going to do number 5 and maybe 6, and then part 3, maybe 7 and 8. Just a lot of stuff. All right, so that's got us started. We took a look at Unit 3.5, which was the limits at infinity, and now we're going to take a look at number 6, which is graph 3.6, which is graph. Okay.